Hi, everybody, and welcome to the sixth edition of this Gemstone mini course. So this time we'll have Chris Judge, who will tell us about variations of geometry and spectrum. As usual in any of those mini courses or the talks, don't hesitate to unmute yourself to ask questions if you have any, or to put them in the chat, which we will relay them to Chris. It's I guess even more critical than in the usual talks that you don't feel like you shouldn't ask those questions. Chris, the floor is yours.
Thank you very much. Thank you very much, John. Thanks for the opportunity to speak. Right, so first I want to thank some collaborators from whom I've learned a lot. I mean, all my collaborators I learned a lot, and in particular, these collaborators, Luki Dede and Sugata Mandal, Craig Sutton, and Sam Lin. I've learned a lot about perturbation theory, um, different issues during our work together, so I do want to point out, however, I'm none of what I say is what they would say. I'm personally responsible for all of what occurs here, um, and I'm not necessarily. This is really for graduate students, so I took it very seriously that I just want to talk to graduate students. So I know they're experts and out there who know in many cases more than I do about this theory. So. Um, uh, and I want the graduate students to ask questions if they have any. Don't, yeah. So this is for you guys. Um, I also want to thank Leverhulme Trust, who uh, gave made it possible that I visited the University of Reading this year, um, and also thank the University of Reading for hosting me. Um, So the lectures, I'm going to give three lectures. The first lecture, is about continuity of eigenvalues and eigenfunctions, and then move on to analyticity of eigenvalues and eigenfunctions. And the last talk, I want to talk about use of transversality in studying how eigenvalues and eigenfunctions vary. And so now let's go to the, yeah, but first of all, yeah, so there's some basic references. There's Cato's Bible. It's a book that every spectral geometer should be aware of and know about. It's called Perturbation Theory for Linear Operators. It's 619 pages long. It has almost 10,000 citations. It's the go-to book for perturbation theory. And so it's the basic reference. Um, but Cato wasn't the first to do perturbation theory, although one might get that impression. There were some very important series of articles by Relic um, in the 1930s and 40s and even 50s. 7 articles with the title "Störungstheorie der Spektralversorgung." And so in Relic's papers, he set the foundations, and then Cato really um, turned it into a huge, well, yeah, it's a pretty monumental work, Cato's reference. Okay, so those are references, although probably maybe the second reference is it's more of research papers than it is a text like Cato's is, a reference book. Okay, so let's start with how I'm going to view spectral theory. So let's suppose we have a omega is a bounded open set. It could be an Rn, or if you want, this could be a manifold with a Riemannian metric. And I'm going to assume the boundary is Lipschitz, so I can use standard elliptic regularity theory. And then, you could take d nu is going to be a Lebesgue measure, and it could be the Riemannian measure if you like. And then the gradient is defined by this equation, where x is a vector field. Okay, so that's a standard gradient in Rn. And then we have L2, the square integrable functions with respect to this measure. And then we have an inner product on L2, which is given by just integration, pairing. And of course, we have a norm associated to the inner product. And then we have a Dirichlet energy, which is, oops, I made a mistake here. This is the norm. Okay. So that's the Dirichlet energy. And then there's the so-called Rayleigh quotient. So this is Rayleigh, which is the ratio of the Dirichlet energy to the norm. And this is defined on H1 Sobolev space 1 functions, take away 0, you can't put in 0. And one thing to note is that this function is homogeneous of degree 0. So it's a homogeneous function. So what we're interested in, from one point of view, we're interested in spectral, interested in the critical points of this functional f. And in fact, what does it mean to be a critical point? It means we're going to differentiate this functional in a certain direction. H is the direction. And no matter what direction we differentiate in, the derivative should be 0. So that's what it means to be a critical point. But then you can compute what that means, and this means exactly that using the definition of the functional, that the pairing of the gradient with u with gradient of h is equal to f of u times u comma of h. Okay, so that's just by differentiating this functional in the direction h. But then if you integrate by parts, you can integrate this by parts, right? So we have this integral. If we integrate this by parts, we find the Laplacian, or negative Laplacian, depending on your point of view. And what this equation says is that if this holds for every h, it means that the Laplacian of u is equal to f of u times u. So f of u becomes the eigenvalue. And there's a little bonus fact is that in this formulation, because I chose h1, this is just the normal derivative. It turns out the normal derivative is 0. So this is the so-called natural boundary condition. Oops. Okay. So so I go through this because, in this perturbation theory, I like to think of perturbation theory in two ways. I want to think about the eigenfunctions of the Laplacian. So this is the eigenfunctions of the Laplacian. But also I want to think about the critical points of this functional. And they're two sides of the same picture. And that's what I've derived here. So now, one thing to note about this picture, on the right-hand side, you can start using, you have this Laplacian, so you can use things like elliptic regularity. And we can talk about, if we're assuming omega is bounded and Lipschitz. So we can then have compactness, Relic, Kondratyov. And then we can say that the inverse of Laplacian plus zi, that inverse, that's the resolvent, is compact for the z's in the resolvent set. And that's enough to say that we have a compact operator and the spectrum is discrete, and L2 is the sum of the eigenspaces. So this is the Rieschauder theorem. So if you have a compact resolvent operator, that's this operator, is compact, then you know the spectrum of this operator is discrete. So you have a bunch of eigenvalues, and then you have, in fact, finite dimensional eigenspaces. each of these eigenspaces is finite dimensional. And
Yes,
they span L2.
there's
Yeah.
a comment in the chat from Leo asking if Laplace is the Laplacian shouldn't in fact map H1
Oh,
to
up
H
here. Yeah,
minus
yeah,
1.
yeah. Yeah, I did this backwards. Yeah. I have a problem with Z2. Yeah, thank you. This should be from, of course, we lose derivatives, so it should be from H minus 1, H1. Thank you. Yeah. Yeah. Okay. Okay, so this is kind of the basic facts. One thing I want to notice about this, and it's going to be important for us, is that so we have this discrete spectrum, is that the actual spectrum is discrete, so it means that it has no accumulation points. It's actually in the positive real axis plus 0. You can have 0 spectrum. But things have to go off to infinity. So if you look at this direct sum and you cut it off at a certain level, you don't allow the eigenvalue to go above a certain value, then that direct sum, that limited direct sum of eigenspaces is finite dimensional. Okay, so only really only finitely many eigenfunctions with eigenvalue less than blah blah blah. Okay, so that's an important aspect of this. Okay, and again, but there's two sides to this picture. One is that we look at the critical values of our Rayleigh functional, the Rayleigh quotient, and then we have the eigenvalues and eigenfunctions of Laplacian. So the basic question I want to ask in this lecture is, do either of these things, critical points on one side and critical values, or the eigenfunctions on the other side, do these things vary continuously with respect to the geometry of your domain? Okay, so this is something that's very different than, say, so if you think of spectral theory, spectral geometry is sort of a mathematical abstraction of quantum mechanics or early quantum mechanics. This is very different than what happens in classical mechanics. You shouldn't expect any continuity. If you have a classical mechanical system and you look at the orbits of that classical mechanical system and you change the geometry of your system, then there's no way, or in most situations, you won't see the orbits change continuously. They'll just change completely. The dynamics is not very stable. But in sort of the quantum mechanical world, in fact, you get a lot more stability than you could ever expect in the classical mechanical world. So that's one nice thing about spectral geometry compared to, say, dynamical geometry. Okay, so in general, we could ask, if we had some sequence of functionals, Fn converging to F, do the critical points of Fn necessarily converge to the critical points of F? And of course, it's very easy to come up with an example which says no. Here's the example. Let's look at this family of functions. Ft of x is x cubed plus tx, where t is some parameter. And for negative values of the parameter, you're going to have two critical points here and here. And then as when t gets to 0, you have 1. And then you can lose them, right? So you can lose critical points when you do these things, right? So critical points can go away. Okay, so now if you have Morse function, then the critical points do stay. Okay, if f is Morse, then nearby Fn would be Morse for large n, and so then the critical points will converge to the critical points. Because the Hessian is non-degenerate. One thing I want to notice is that this example, okay, there's another example. There's another u squared. There's another example question in the chat. Let's see, what is that question about? Yeah, it is equal. I can take h equals u, and everything will be fine. Yeah. Okay. But if f is Morse, then I do this. But if you can also look at the Rayleigh. So now let's look at the Rayleigh quotient. If I restrict it to the unit sphere, it is Morse if the eigenspaces are one-dimensional. That is, if I have simple eigenvalues, then this function would be Morse. And then you could say that the critical points converge to the critical points, and you'd be in, you could say that you would have eigenspaces converging to eigenspaces. But the problem is multiplicity. So, and we'll see in a moment, I'll give an example where things can go wrong. Okay, so it's the fact that, so my point is that the fact that critical points, that the functionals converge doesn't necessarily imply that critical points are going to converge. But in the case of Laplace eigenfunctions, we have a little bit more information. Okay, so first of all, let's go back to what we had before. So let's go back to, we have a vector space. This is a more general situation. Just suppose we have a vector space. We have an inner product like the L2 inner product. We have a symmetric bilinear form. Okay, of course, every symmetric bilinear form can be written as inner product, this inner product with a matrix A, or in general an operator A, but let's just think about finite dimensional situation now. This is sort of the analog of our Laplacian. And then we want to look at the ratio of the bilinear form over the inner product. So this is the analog of taking the Dirichlet energy divided by the L2 norm. Okay, so this is a toy model from which we can work. If we think about a finite dimensional vector space, we can think about perturbation theory of eigenvalues and eigenfunctions in this situation. And it turns out by the same analysis we did before is that the critical points of this toy model, Rayleigh quotient, are the same as the eigenfunctions of the operator A. Okay. Okay, so in this situation, also in the case of Laplacian, we have this minimax principle, which tells us that here's one formulation, and I'm specializing to the case, or I'm emphasizing the case of eigenfunctions as opposed to eigenvalues. So let's fix some m bigger than 0, and I want to look at all the critical points whose value in absolute value is less than m. So here I'm allowing for actually negative eigenvalues as well as positive eigenvalues. And so I'm going to set this to be equal to em. And the reason for E is because this will be the same as the eigenspaces, the direct sum of the eigenspaces, where mu is less than that cutoff m. Now, when I write these brackets here, I mean the span of. So I'm taking the span of all critical points with whose value is less than m in absolute value. And that's going to be the same as the direct sum of these eigenspaces. So I'm taking all the eigenspaces up to some value m. Okay, so that's what I'm going to call E, or E to the m. I'll take the minimax principle says, well, look at the following function. I'll take W and V, consider the map W goes to G of W, where G of W is defined to be the maximum of F of W. Okay, so the maximum value. So I'm taking, by this, I mean I'm taking the image of W under F. So that's some collection, and I take the maximum or the supremum. It turns out to be a maximum. If we're talking about a compact, F is homogeneous and W is compact. Essentially, I mean, because it's homogeneous, it's really a maximum. Okay, so the minimax theorem says that this set E, or this vector space E, is the unique minimizer of this function over all the W whose dimension is the same as E. Okay, so you look at all the different subspaces. Oh my gosh. And you vary the subspaces, and you see who's the minimizer of this. So that's the minimax principle. Okay, and it's also unique. The eigenspace, the sum of the eigenspace is a unique such thing. Okay, so this is different. It's not, so now this is more than just saying critical points. This is sort of characterizing how we get the critical points. And now to move towards continuity, we can apply the following lemma. So suppose you just have, well, maybe I should say some words about this space first of all. So this thing, the space of all W, where the dimension is constant, is really the Grassmannian. And it's the Grassmannian of dimension of E planes inside our vector space. So, and this is really compact, okay? So, and I'm going to apply, so that compact space, I'm going to apply the following lemma. So suppose X is any compact space, and I have a sequence of functionals converging, or functions, continuous functions converging in the topology of continuous functions, the sup norm topology. And suppose that I have a sequence xn going to x. So in my application, these would be planes, one moving to the other. Then if xn is a minimizer of, say, gn, then x is a minimizer of g. So minimizers converge to minimizers. Okay. By the way, I'm going to use MZR to abbreviate minimizer to make things, yeah. So instead of writing minimizer all the time. Okay, so that's the basic lemma, and that's enough basically to tell us that that this set it varies continuously under perturbation. Okay, so let's see how that works. Well, first of all, let me make a remark. I'm doing this I'm pretending I'm in a finite dimensional case, but the thing that makes this work in, say, the context of Laplacians or second order elliptic differential operators on a bounded domain is this fact. So my space EM, the sum of the eigenspaces, it's actually, because eigenfunctions are very regular, they actually belong in higher Sobolev spaces than just H1. So they belong, for example, in H2. So E belongs in the set of functions that satisfy this inequality. Okay, so here's this is the H2 norm, And because I'm taking the eigenvalues are less than m, I know that everything H2 norm is going to be less than m plus 1. And this is actually compact in H1. So I can actually restrict my the functionals to this smaller set. And this would be my x. Okay, so given this, okay, given this lemma, now let's prove the following. Um, so again, there's one little caveat I have to do, which is that I have to assume that I take a value, a cutoff value, which is not a critical value. So here's the picture. This is sort of the mu parameter, the eigenvalue parameter. And I have these functionals. Fn is converging to f. And then these are my different eigenvalues. So for f, I have these two eigenvalues. And then for Fn, I may have all these eigenvalues. And the idea here is that if I take the direct sum of the eigenspaces associated to those four eigenvalues, they converge to the direct sum of the eigenspaces associated to these two. Of course, and so that's this statement. Okay. Of course, this statement actually gives you a little bit more, because you can also look at a cutoff between the original, between this eigenvalue and that eigenvalue. You can look at the cutoff m prime here. And then if I know that this direct sum converges, the direct sum of these two converges to this, then by just taking the complement, I can see that these two eigenspaces converging to those two converges the eigenspace for that eigenvalue. Okay, so it provides more than just, but you have to actually look at the and cut between. Okay, so that's the statement. Here's the proof. Yeah, so here's the proof. So first of all, yeah, so the dimension of En is you can assume that this dimension of En is constant. I'll take that constant k up to some subsequence. Now there is some little thing in the infinite dimensional case. You have to make sure that the dimension of En is bounded, but the fact that the spectrum is discrete, you can work with that to see that, and the fact that the Fn's and also the Gn, the Fn's are converging to F tells you that that's going to be the case. One thing I should say here is, before maybe continue, is that really Fn converging to F is really implying that Gn is converging to G, where G is the maximum over of F and over a particular subspace W. Okay, so now if I take, so let's assume that therefore that we have a constant, and so now take En, and we can also assume that En converges to E star, because the space over which we're looking is compact. We're looking at this Grassmannian, and it's compact, and so we get up to a subsequence. We get a limit, and then the game is to prove that E star is, of course, the same as E, and right. So then, yeah. So the lemma above tells us minimizers go to minimizers, and so therefore E star is a minimizer on k-dimensional subspaces. But the problem is, the technical issue is that we don't know a priori that this is a k-dimensional subspace. If E is a k-dimensional subspace, then the uniqueness will tell us that E star must be equal to E. They're both minimizers, and there's a unique minimizer in that dimension. So I need to know that, in fact, E has dimension K as well. So there are two cases to consider, okay? And I need to get rid of this case, and I need to get rid of this case. Okay. So um, if E star has dimension larger, well, if it has larger dimension, then its value, the value of the functional f is going to be larger. It has more vectors, so it has a potential of having a larger value. So G is going to be larger than, or equal to G of E. Okay? And if equality, then I've got if this was equality, then I could choose other subspaces of E star, okay, which have the same value, but E is a unique minimizer, right? So therefore, that gives me a contradiction. Okay. And if E is bigger, then I can use the fact that Gn converges to G to tell me that Gn of E is smaller than Gn of En for large n. Okay, so that tells me that this case is not possible. Okay, and now if dimension of E star is less than the dimension of E, well, that means that there's some vector in E which is not in E star. Okay, but then for that vector, I'll have that f of V is less than my cutoff minus some epsilon. I have a strict inequality, so I can find some epsilon that fits in between. And that tells me that for large n, Fn of V will be less than n minus a slightly smaller gap, epsilon over 2 for large n. But that's a contradiction to the fact that E star, that I had a minimizer, that this was a minimizer, that En was this guy was a minimizer. Okay. Okay, so anyway, so you, in either case, you play this game with minimizers and you show that both of these cases are not the same, therefore, both these cases are not possible, therefore, the dimensions of E star and E have to be the same, but they're both minimizers, and minimizers are unique by the minimax principle, so therefore E star has to be the same as E. Okay. Okay, so that's the proof. I should maybe stop for a question. Are there any questions?
No, you answered the question quickly after the question was asked.
Okay, good. Right. Yeah, we're doing, yeah. So Grassmannians are finite dimensional. Grassmannians are compact. Right. So, I mean, yeah, one of the important things is we're talking about the functional f is homogeneous, so it's determined by its values on the unit sphere, or the maybe better to say, take the projectivization of your vector space. And so this functional is defined on the projectivization, and that makes sort of things compact. So in that sense, homogeneity is very nice. Okay, right. So okay, so that's that. Now, okay, so that's the good news, and then the bad news is sort of the following example. So let me first, without, I mean, okay, I've written down all these formulas, but maybe it's much easier to explain in the idea. It's just a marvelous idea of relic. So you know, if you have, so let's think about the finite dimensional situation, 2 by 2 matrices. We're talking about the vector space is just R2. And we, of course, know how to diagonalize a symmetric matrix. And the way we do that is we have a pair of unitary matrices, which are basically rotation matrices, if you like, which we conjugate our original matrix to get a diagonal matrix. And in particular, if I take any symmetric matrix and I conjugate it by unitary matrices, then I'll end up with also another symmetric matrix. So I can start with something, a symmetric matrix, which is nice. Like I can start with the matrix, this matrix, T minus T, nice diagonal matrix. And then I can apply a rotation. I can conjugate by a rotation matrix. Here, the rotation is this. And so I get a family of matrices by doing that. And now, if I just, so the idea is if I just conjugate by, if I conjugate by these matrices, I'm sort of spinning the bases around. So, I'm rotating the, I have two distinct eigenvalues, t and minus t, and the one eigenspace is going to be this, the column, and the other is going to be the other column. And basically, as I vary t, these two eigenspaces are being moved around, so they're getting rotated as I vary t. And so I have this, but they're not in the same eigenspace, okay? But when t gets close to 0, they are. I mean, when t is 0, this function is, so the key thing to put, this is a continuous, so at is continuous. And the reason is because it's the usual thing that if you have t times cosine 2t, this is a bounded function. T is going to 0, so this is going to be continuous even at t equals 0. So this is continuous at t equals 0. So you get this family of matrices, continuous t equals 0. But as t goes to 0, these two eigenvectors rotate around infinitely often, right? So in fact, neither of these eigenvectors converges as t goes to 0. Right, so you have this very nice family of continuous family of matrices, even at t equals 0. But the individual eigenvectors do not converge. Okay, so eigenfunctions do not converge. And who's to say that this has not come from some spectral application with some operator? It could be this could be part of the projection onto some eigenspaces of some differential operator. Who knows? I mean, why? So this could happen in your problem. So why doesn't this contradict what we just discussed with this theorem above? It says eigenspaces converge to eigenspaces. Is it okay to ask a question of everyone? The students? I'm looking for your answer in the chat. Yeah, so let me answer the question. So the thing is that when you look at these eigenvalues, suppose this is the eigenvalue 0, we have the eigenvalue t, we have the eigenvalue minus t, and when I look at first, to do this, the theorem above, I have to look at um, the places where f of m is, or sorry, f of u. I'm looking, the space E is defined, EM is defined by the places where f of u is less than m. So I can fix m, but when I talk about the convergence, I have to talk about the convergence of the sum of this eigenspace and this eigenspace. It converges to the eigenspace for t equals 0, which is perfectly fine, right? So I had to fix that m to begin with. So the theorem says that the direct sum of these eigenspaces is convergent. And that's perfectly fine because the direct sum of these two things, these two vectors, they span R2. And so the theorem is just saying R2 converges to R2, which is perfectly fine. Okay, but the individual eigenfunctions do not. Okay, so you have to be careful in what you mean by eigenfunctions converge, etc. Okay, any questions about this example? Oh, and one last thing is that you can make this example smooth. So instead of using t and minus t, you can use e to the minus t squared and e to the minus t squared here. Oh gosh, squared. And that allows you to replace e to the minus t squared, t with e to the minus t squared. And then this times this is a smooth function at t equals 0. So it has nothing to do with any non-differentiability. This is a perfectly smooth function, and but it's still, its eigenvector, individual eigenvectors do not converge at all. Right? They just keep wrapping around. Okay, so so now I want to, some people probably in the audience know there's a different way of thinking about the eigenfunction, eigenvalue convergence, and that's via the Riesz projector. So it's a different point of view, and it's actually emphasized by Kato. Here, so I just want to mention it. It's a different sort of development of the continuity, and it will be useful in the analyticity part of perturbation theory. So let's suppose we have another operator. It could be a matrix, could be a Laplacian. It's mapping a vector space to a vector space. The resolvent set is the set of places where it's not invertible. It's the complement of the spectrum. And a nice fact is that the actual resolvent is holomorphic on rho of A. Okay, so it's a holomorphic function. And that allows you to talk about things like line integrals and such. In particular, let's take a disk centered at some point, and let's take omega to be the, sorry, gamma to be the boundary of this disk, and let's orient it in usual fashion clockwise, and then we can define this operator. So it depends on the original operator A and the choice of gamma. And I'm assuming actually gamma is completely inside. There's an assumption here that gamma is inside the resolvent set. It's inside of it. I don't want to hit any eigenvalues. And then you can apply, you can get at the Riesz projector is defined as minus this integral, oh, I forgot, a 1 over 2 pi I, 1 over 2 pi I, and of the resolvent. So dz. So this line integral, and there's a u here. So this is just a vector. This is a vector, and I'm just integrating a bunch of vectors. I'm averaging them, if you like, over this curve. Okay, so that's the Reese projector. And it turns out it's just the magic of complex or functional analysis is that this is a projection operator in your vector space. And it projects exactly onto the sum of all the eigenspaces that lie inside the ball. So, sorry, that all the eigenspaces associated to eigenvalues that lie inside the ball. Or more generally, if you have continuous spectrum, it's also the sum of the spectral measure of that part, right? So it's more general than just the eigenspaces. But in our context, we're just doing eigenspaces. And so you take the eigenspace associated to mu2, the eigenspace associated to mu3, the eigenspace associated to mu1, you take their direct sum, and that's given by, you have a nice projection onto that direct sum, and it's given by this operator, okay? And so from then, this gives you a different way of thinking about this convergence of eigenspaces. You can sort of fix the gamma. We're going to fix gamma. And suppose that I have the resolvent is converging to the resolvent. So the resolvent of AN is converging to the resolvent of A. If you can show that, then the integrals will also converge, meaning, and since the integrals converge, you can show that the images of those integrals, those integrally defined operators, projection operators, those images also converge. Okay, notice gamma is fixed here. So what's happening is the mu's are allowed to move. So the mu's can move around. Gamma is fixed. Okay, so a sum of eigenspaces converges to a sum of eigenspaces, just as before. Okay, so that's a different perspective. Okay, any questions about that? Okay, so now I want to get into an application. So I promised some applications, but I don't think I'm going to be able to do much more than sort of the following. Yeah, and also I want to talk, this application involves a different perspective on, it enlarges the perspective that we're dealing with. So it has to do with dumbbells. So the perspective is that this eigenvalue convergence also works in situations where the topology of your manifold or your domain may change. So it's so robust, the eigenfunction eigenvalue convergence, is that you can really just tear apart your domain at times or do all kinds of crazy things to it. I wanted to say, with respect to this, if the resolvents converge, I wanted to point out there's a very nice paper of Rauch and Taylor. Here it is. I wrote it here. And there it's about wild perturbations. So you actually really do you take domains and you really make them bad, and you still get this sort of convergence, and which implies that the eigenfunctions also converge. So that's a very nice paper. I think it's 1970 or something. But a very basic example of this is given by dumbbells, and this dumbbell example goes back to Courant and Hilbert. So you can, it may even go back farther. Maybe someone can point out an even earlier place where dumbbells were used. Okay, but here's the idea: is you have two different domains sitting inside maybe R2, and we have omega minus and omega plus, and we take a disjoint union of these two domains. The first eigenvalue is 0, but it has its two-dimensional eigenspace. So here I'm kind of sticking with my previous notation. So I'm taking the next eigenvalue called mu2. I divide by 2 to get so here's 0. I have which is mu1. And then I have mu2, which is the next eigenvalue. And I take my cutoff to be m, to be half of that. And then em will be basically the eigenspace associated to mu1, which is, well, I can take the characteristic function on this, and I can take the characteristic function of that. Both of those are in the kernel of the Laplacian. The Laplacian of a constant function or a locally constant function is 0. So I have a two-dimensional eigenspace, the span of this guy and the span of that guy. Okay, so to create a dumbbell, what I do is I put in a little tube that joins omega minus and omega plus. And I want to make this tube as small as possible. So I'm going to have this width of the tube is going to be epsilon. So I have omega minus and an omega plus, and then I put in a tube. So now I want to look again at EM, but now for EM for epsilon, now for the new domain, which has been connected by this tube. And it's still going to be two-dimensional. So here's the first, I don't have two different, I only have one locally constant function. Before I had two locally constant functions. Now I have one because I've connected the two regions. But I do have, there is something that makes up for the lack of that second locally constant function. And that's going to be a function which is approximately a constant function here and a constant, say, plus 1 on this, minus 1 on this side, and plus 1 on this side. And then in between, it's going to be a linear function which interpolates between minus 1 and plus 1. Okay, so there's, in the band, I'm allowed to put a function in like that. Now, U1 epsilon is not exactly that, but that's sort of the model for it. This is sort of a quasi mode for that. What's happening is that because this tube is so small, you can get away when you integrate the gradient to take the Dirichlet energy, that's still going to be small, even though you have some actual gradient, because it's so thin. When you actually integrate, you get something small. So it gives you very small Dirichlet energy. So you get something that has eigenvalue close to 0. So the eigenvalue here is not going to be 0, but it's going to be close to 0. But remember, I'm just trying to stay below m. So I'm allowed to go a little bit above. Okay, so these are and the picture is something like this. So here's epsilon. Epsilon's going out this way. The eigenvalue parameter is going like this. And as I move the eigenvalue parameter, the epsilon goes to 0, of course, the first eigenvalue is 0, but the second eigenvalue will eventually go towards 0. Okay? You'll be able, this U1 will start having smaller and smaller Dirichlet energy. And I avoid the next eigenfunction, which is, okay. So that's so in this case, what's happening is the eigenfunctions, this space, is actually converging in a sense to that space. So I still have, even though, when I actually let epsilon goes to 0, this topologically connected region becomes disconnected in a sense, because now there's really nothing left of that connection. Even though I've in some sense changed the topology, the eigenspaces still converge. Okay, so that's the point of this example. Okay, now so this example has been well studied, and it's by lots of people and has motivated lots of stuff. But one application that I love, it's one of my favorite theorems in spectral geometry, is, and it's really a foundational result, is the following theorem of Coulomb-de which I'll end on. So basically, Coulomb-de said you can given any sequence of numbers, a finite sequence of numbers, you can realize it as the spectrum of some. Um, this is the Neumann problem. I'm only considering the Neumann problem here. You can realize it as the spectrum of your Laplacian on some domain, even simply connected. You can find some simply connected domain which has those first k eigenvalues. You specify the eigenvalues, and Coulomb-de gives you the domain. And so how is this an application? Well, the idea is simply that you take, you're going to choose a lot of domains. You're going to choose a lot of domains depending on the k. And then you're going to connect them with little tubes. So you'll make this what's called a generalized dumbbell. So you'll have lots of different domains. You connect them with lots of tubes. You can think of, in fact, this is a graph. You can take sort of the dual graph, or you can take a graph of sort of objects like this, where each vertex corresponds to a domain, one of your omega i's. And then he showed, then there's some work that came before. I mean, basically it was Colbois, I think, who first recognized this, is that in the context of hyperbolic surfaces, is that you can understand how the spectrum, how the eigenvalues near zero, this whole, you can make a study like this, and you can see that, understand how the eigenvalues converge to zero, and use that to try to choose the right geometry to produce these eigenvalues. Okay, there's another additional idea that goes into this, which is transversality, but the first step is an analysis like this, but in the generalized situation where you have many domains connected by many tubes. Okay, so maybe I should stop there. Yeah.
Thanks a lot, Chris, for this first lecture. Do we have some questions for Chris after this first day? Somehow, I was expecting to see this last example in the last lecture, not in the first lecture, I guess.
No. I mean, yeah, I mean, I could talk. I mean, there is a second part to this, the Coulomb-de, which is transversality, but I don't think you get going until. I mean, maybe there are people here who actually participated. I don't know, but in this kind of thing, but there, you first have to understand how the spectrum how eigenvalues converge to zero. So you're going to have the eigenvalues. So you have all these different eigenvalue branches going to zero, and you have to understand. There's a basic lemma which is going from here to here, which is about small eigenvalues, petite le lim, yeah, small eigenvalue lemma. It's called that. And and then so what you end up showing is that the eigenvalues of what you show is that basically the one quadratic form is given by epsilon times another quadratic form. So I'm going to call this maybe q plus epsilon O of epsilon squared. Where this is for a graph, is the graph Laplacian. And then and then you divide both sides by epsilon to get Q epsilon is equal to Q plus O of epsilon. So, so, so this is the quadratic form associated to the Dirichlet Laplacian, Neumann Laplacian, but restricted to the small eigenvalues. So I restrict my Dirichlet energy to small eigenvalues, or the eigenfunctions associated to them. And this is the graph Laplacian. And I choose this graph Laplacian to have these eigenvalues. And then so that means that basically the eigenvalues of this are very close to the eigenvalues that. Okay, so then there's transversality has to be applied to say that by adjusting the different domains, you can actually get this to be right on for some epsilon prime. So you can get rid of the O of epsilon. And then you're done, because basically this is a rescaled Laplacian. You can rescale the domain so that, in fact, this is equal to some Laplacian.
Yeah.
Anyway, so yeah.
Yeah.
But so
there was a
the last part, transversality, is extremely important, but it's
well, there was a question in the chat, but which was essentially answered by this answer you just gave right now. Are there other questions for Chris after this first lecture?
I guess just a small remark that you also used, there is a simple result that for a complete graph, you can get any string A1 through AK, but that's not so difficult to prove.
Right. Yeah, I should say that you can actually get, the eigenvalues.
Like, not every graph is going to work, but complete graph has all the edges are there, so it has the most room to play.
Right. No, there's several. I mean, I gave a very, I mean, this work is over a string of different papers, by the way. I gave a very quick proof, but there are many different moving parts. I mean, it's an amazing piece of work. It has many moving parts, and dealing with the graphs themselves, of course, you're right, is a part of it. Yeah.
Do we have any other questions or remarks? All right, we'll resume on Monday at the same time, where we will discuss analyticity. Until then, hope you have a great weekend. Thanks again, Chris, for this first talk.